And our last speaker of the conference is Eran Nevo, and he'll talk about vertex-spanning planar Laman graphs in triangulated surfaces.
First, I want to thank the organizing for having me here. It's been a wonderful conference so far. And thank you all for coming. Feel free to ask questions. The topic is rigidity with few locations, and the subtitle is the title of a recent paper with Simeon Tarabikin. We will get to that in the second half of the talk. So let's start with what is infinitesimal rigidity. So you're given a finite simple graph on n vertices and a mapping of the vertices into Euclidean d-dimensional space. Let's also assume that if you put these vertices generically, they affinely span the entire space. So n is at least d+1. And now this framework, the pair GP, is called infinitesimally rigid if an associated rigidity matrix Rg of P has the maximal rank it could possibly have, and which is dn minus d+1 choose 2. So let's give details here. So the matrix has dn rows and has a column, one column per edge. So for the edge ij, we put in the d rows for the vertex I, the location of ipi minus the location of j, and vice versa for the d coordinates for j, pj minus pi, and zeros for the other ones. So that's the matrix. And you see that if you perturb P to be what we call generic, so that all of the dn entries are algebraically independent over Q, the rank can only grow. And if we take the graph and, I mean, we keep the same ground set, but we add edges, then this means that we add columns to the matrix. So also the rank can only grow. So the maximal rank that could possibly you have is when you take the complete graph and with generic P, and then one can simply compute the rank, and it's this number, dn minus d+1 choose 2. And then we say that the graph is generically rigid, or briefly just d-rigid, if for a generic P, the framework GP is infinitesimally rigid. So that's the notion. And okay, if it happens for one generic P, it happens for all of them, the rank would be the same. So here are some examples. Let's take our graph now is the triangle, and we embed into the plane. So let's first consider a degenerate embedding, so the flat triangle. And so here the rank wouldn't be the maximal possible because there is a non-trivial element in the left kernel of the matrix. So if you think what are the elements in the left kernels, it means that you assign a velocity. You can think of it as a velocity vector at each vertex. And the condition is that at every edge, the difference of velocity would be orthogonal to the direction of the edge. This is just by multiplying that velocity vectors with the rigidity matrix. So here you see that we put 0 velocities to 2 vertices, and then a non-zero but orthogonal to the direction of the 2 edges emanating from that vertex. And so that's a non-trivial vertex element, sorry. Okay. But if you put a generic location, then you will get infinitesimal rigidity for the triangle in the plane. Second example, so now consider 2 triangles glued along a common edge. So in the plane, this graph is too rigid, but in 3 space, it is not. So one thing is you can think about a motion and then the non-trivial infinitesimal motion associated to it, but you can also just make the edge count and see that you don't have enough columns in this matrix. You have 5 columns, but the rank should be 6. And the third example gives us closer to the topic of this talk. So this graph at the bottom, this Indian peacock, is connected. So connectivity is exactly the same as one rigidity. But not only it's a bird, it's also a tree. So in particular, it's bipartite. And now we can rigidify it using fewer locations. So if you put all of the, we map all of the black vertices into one location and all of the white vertices into another location, the resulted rigidity matrix will have all of the columns independent. So the rank would be n-1, and you will get rigidity even with this degenerated P. So this leads us to the following definition. So you're given the graph and a finite set in R to the D. We say that G is A rigid. So think that this is A rigid if there exists a mapping of the vertices into this subset A, such that the resulted framework is infinitesimally rigid. And now we are interested in families of graphs that are generically D-rigid, and we will try to rigidify them using few locations. And let's also consider then the filtration of this family. So Fn is the subfamily of all graphs in the family F with at most n vertices. And here's the definition, that's the key definition. So we said that this family of graphs F is D-rigid with C locations if you can find a subset A of R to the D of size C, such that every graph in this family is A-rigid. And now we try to make this C as small as possible. And so this we call CD of the family. That's the minimal C that works. So we are interested in families where this CD of the family, interesting families of graph when this is bounded, so infinite family, but still that the CD of it will be bounded. And if it's not bounded, then what is the growth of it as n tends to infinity? So CD of Fn when n tends to infinity. So for a start, let's us consider the family of all D-rigid graphs. So again, for D equals 1, these are just the connected graphs. So Fekete and Jordan showed that C1 of F1 is 2. That's the argument I showed you before with this peacock graph. So the graph is connected. It's one region. When it's connected, you take a spanning tree. It's bipartite. You do the same thing. And they show that C2 of F2 of n grows at least as root of n. And actually, the argument shows it's for any d at least 2. But for sake of time, let me skip the proof that is mentioned here. And Király showed recently that the right order of magnitude of C2 of F2n is indeed root n. Let's consider now the family of planar graphs. So Király, answering a question by Whiteley, that showed that C2 of the what's called planar Laman graphs, namely planar graphs that are minimally too rigid, minimally with respect to edge deletion. And so they can be rigidified with 26 locations, all of this family. This question of Whiteley appeared in a paper by Karima Di Prasinto and myself, where we show that if you consider all maximal planar graphs, namely those that triangulate two-dimensional spheres, then you can rigidify all of them in R to the 3 with just 76 locations. Probably that's not a tight bound, but the point was that it's a finite number. And further, you can, okay, maybe. Let me tell you the algebraic statement that allows for inductive proofs of both of those two results. And the point there is that when you have a rigid framework, now you want to move the vertices one by one into your set A. That's our goal. And so assume that GP is infinitesimally rigid and that a vertex V of G has a degree C. And now consider a subset of R to the D with, which have generic coordinates, but such as the subset is big enough, namely of size at least D plus C, choose D. And then the statement is that you can find a point in A, some element A in A, such that if you now modify the embedding so that all the vertices stay in the same locations, only this one vertex V is mapped to A, then this new framework will also be generically rigid. And now if you iterate this, you see that it says an A rigid graph. And how to do that? So what does it mean? So let me sketch the proof. What does it mean that the graph is infinitesimally rigid? You look on the rigidity matrix, and it means that you can find a minor of size dn minus d plus 1 choose 2, where the determinant is non-zero. So look on this minor, but now replace P of V by a kind of a variable locations that we will later we will specify what it is. So you replace P of V by x1, x2 up to xd. And now compute the determinant of the resulted minor. So this will be a polynomial of degree at most C, because there are at most C columns involving this vertex V, and of degree in D variables. So degree at most D in D variables. So namely, it's in a space of polynomials of dimension D plus C choose D. So, but it's not the zero polynomial. So if you try it on so many points, so many generic ones, for one of them, it will give a non-zero determinant. So the rank would be fine. And that's the proof. All right. So now let's consider graphs on surfaces. So let M of G denote the surface of genus G. And let F of MG be the family of all the graphs of that triangulate M of G. So Vogelsanger in his thesis showed that all of those graphs are 3 rigid. So in our notation, it means that C3 of this family, F of MG, is countable, Aleph 0. And what we want now is to rigidify them with few locations. So with Karim, we showed that C3 of this family is at most some constant, and the bound that we got grew to infinity with G though. But it's a finite for every given G. And similarly, if you look on all Laman graphs that embed in MG, Király showed that you could rigidify all of them in the plane using only a constant number of locations. But again, his bound grows to infinity with G. So it's an open problem whether there's a uniform bound that works for all genus together for both of those families, once in R3, once in R2. Okay, so an intermediate problem that is, okay, we try to rigidify the graphs that triangulate surfaces, rigidify them in R3, but it's easier to rigidify them in the plane. So let's try to do that with a uniform number of, with some bounded constant number of locations. And a way to do it is, if the answer is yes to the following question: does every graph of a triangulation of the surface of genus G contain in it a vertex-spanning planar Laman subgraph? Because if so, then this subgraph by Király can be rigidified in the plane using only 26 locations. That would solve the problem. So we don't know how to show it for, and whether it's true for all surfaces, but we showed it together with Simeon Tarabikin that the answer is yes, if the Euler characteristic of the manifold of the surface is non-negative. So this amounts to 4 different surfaces: the sphere, where Király showed it, and for the other ones, we show the following stronger statements that in particular implies the statement I mentioned before. So we show that for every triangulation of the projective plane, you can find inside a spanning disk. In particular, the disk, it's planar. So you can find a planar Laman spanning graph inside it. So you can find even this 2-dimensional subcomplex inside. We need only a 1-dimensional. And for every triangulation of the torus, we show it contains a spanning cylinder. Again, it's planar. And every triangulation of the Klein bottle also contains some spanning planar 2-dimensional subcomplex. It is either a cylinder or a pinched disk, or the connected sum of 2 triangulated disks along a triangle. So you identify two triangles from one disk with the triangle in the other disk, and then you remove the interior. That's the connected sum operation. So this is again planar, because you could fit, say, all of the second disk inside the triangles that you emptied in the first. Okay, so for all of those, we can apply Király's result and rigidify all of the triangulations of these surfaces with using 26 locations. Okay, so the way the proof goes is to reduce the problem to irreducible triangulations. So we say that a triangulation of a surface is irreducible if the contraction of any edge in the triangulation would change the topology of the space. But you can phrase this condition also combinatorially. It just means that every edge is contained in some empty triangle, where you have the three edges, but the triangle itself is not part of the triangulation. You can see, for example, if you have a sphere with an equator, which is a triangle, then you construct an edge, you will get two spheres glued along this edge that survived from the constructed triangle. So we altered the topology, but that works in general. That's the condition. Okay, so Barnett and Edelson show that all for any surface, it has only finitely many minimal triangulations. So for the surfaces that I mentioned to you earlier, where we have the result, the set of all minimal or finitely many irreducible triangulations. Sorry, so minimal and irreducible is the same. Okay, so it should be irreducible. Irreducible triangulations. The set is known for those spaces. So for projective plane, there are only two, and you see both of them here. And here are some spanning disks inside them. For the torus, there are 22 irreducible triangulations found by Lavranchenko. For the Klein bottle, there are 29. So 25 of them were discovered by Lavranchenko and Negami. They thought that, and then later Sulanke completed the list, found 4 that they missed. So here you see some of the, so the top 10 are some of the 21 irreducible triangulations of the torus, and the shaded areas, you see how we pick cylinders, spanning cylinders inside them. So it's a torus, so you identify the top and bottom and the left and right sides. Okay. So you get these cylinders, and on the bottom you see some pinch disks in 2 of the 4 more complicated, in a sense, triangulations of the Klein bottle. I'll explain later about them. Okay, so we find desirable spanning subcomplexes in the irreducible triangulations. So what we want to do now is to have some procedure how to extend it as we reach the triangulation at hand from the reducible one by doing vertex splits. That's exactly the inverse operation of the edge contraction that I mentioned before. So here is edge contraction. We contract the XY edge to a point, and if you reverse the arrow, that's called a vertex split. So what we want is to have a theorem like that, so that you will have an irreducible, inside our triangulation, we will have a spanning subsurface of the type that is suitable for that particular, for the surface at hand. So a spanning subsurface. And now what we want is that as we do the vertex split, to be able to extend it, this surface to a bigger surface of the same homomorphism type that will capture also the new vertex. And moreover, that this new subsurface itself will be extendable for the next iteration. Okay, so that's the goal. And indeed, we have the following result that sometimes you can do it. So here is the definition of extendable I just mentioned. And the homomorphism type is preserved. So I didn't say how we, sorry, let me go back. So when we do this, when we extend from the old subcomplex to the new subcomplex, from the old subsurface to the new one, we do it either by doing a vertex split on the subsurface, or the other option is this, which is we cone over an interval in the boundary. So in any case, we preserve the topology and we capture all the vertices. Okay, so here's the main theorem, this extension theorem. So let delta be a triangulation of the surface of genus G, and consider a vertex spanning subsurface in it. Suppose we already found one. So then this subsurface is extendable by, when we do this vertex split, is extendable if and only if it includes at least one edge of the from every triangle in delta. Okay, so we don't want to find a triangle in the triangulation where none of the three edges is in our subsurface. Then it's extendable, and moreover, we want that the extension will also be extendable, and indeed it's possible. In that case, if it's extendable, we can indeed extend it in an extendable way. Okay, so the easy direction, which is actually less useful for us, but just for it's part of the theorem, is that if we have a triangle, okay, so here the shaded parts are part of my subsurface, and so you see here a triangle where no edge of it is part of the spanning subsurface. Then if you do this vertex split, there's no way to extend the subsurface. We are more interested in the other direction. When this is not the case, how to extend. In any case, so with this theorem, whenever we can find in the original irreducible triangulation a spanning subsurface, we are done for all the triangulations that will come up of it. So I showed you before how we do it in the projective disks in the projective plane and cylinders in the torus, and you can do it also for the other ones. And for the Klein bottle, you can do it for the early found 24 triangulations, but you cannot do it for the last 4 what's called Kreskoska triangulations. For this, we will have another thing that we will soon show what to do. Okay, so how to extend from S here to S prime here. So we look on the vertex split. So to describe a vertex split, we look on the link of this vertex V that we are going to split, and describing the split is just telling 2 vertices on it. The boundary is a circle, 2 vertices on it where the split happens. So these are here X1 and XK in the picture. Now, if you look on the star of V, so part of it consists of these consecutive triangles, and the other part consists of these boundary edges of the subsurface. And altogether, so there will be a gap here of an edge which is not part of the, okay, so this is part of the subsurface S, and also this. And those 2 edges are not. So now what to do depends on whether X1 and XK, if they are on this boundary part or on the triangles part, or one here and one there. If both of them are on the boundary part, we do this coning over an interval in the boundary. That's what we do here. And if at least one of them is in the triangle part, then we do a vertex split. Here you see in one of the cases the vertex split, and here is in the other cases. So that this, and you can exhaust all these cases easily. Okay, so we are left with those 4 problematic irreducible triangulations. You see that in both of them, this part is an RP2, this part is an RP2, and they are glued along this missing triangle, the ABC. Now, as we do the vertex splits, so we start with them and we do vertex splits. If along the vertex splits, this missing triangle ABC is preserved all along, then what we can do is pick a spanning disk on that side, pick a spanning disk on that side, so that these spanning disks will contain also this ABC triangle. And then just as we argued on each of the pieces before, and we will have in the end connected sum of 2 disks, and we are done. So what's left is the case where in one of the vertex splits, it may happen that it splits also the missing triangle, making it a 4 cycle. The question is what to do then. So that's the problematic thing. And okay, this I actually already explained. And there we show some kind of a commutativity claim that you can rearrange the split so that first you split, the first vertex split you do actually extends this missing triangle to a 4 cycle. And now how to resolve this? So what we do in this case, to start with, we start with a pinched disk, say that we vertex split C. So we look on this pinched disk at C, and now we resolve the singularity in this manner. And you get a cylinder, and from now on, you can apply the extension theorem. Okay, so that's how the proof goes. And just to finish off, so the first 2 questions we already talked about. The third one is you can consider also triangulation of high-dimensional manifolds or spheres and check about this rigidity with few locations there. And what I think is maybe the most interesting and open here in this line of research is take now D more than 2. And the question is whether CD of FDN is little o of n. We showed it's at least root n, but the question is, can you save significantly in the number of location? This is somehow, the idea here is to understand the role of genericity in this theory of framework rigidity. Okay, so thank you.
Thank you very much. Any questions? Okay, I guess then thanks again. Also, let's thank all the speakers and all the poster presenters again.